Hello, my name is Panayiotis Danassis, and I will be presenting our paper entitled Differential Privacy Meets Maximum Weight Matching. Maximum weight matching is one of the most fundamental problems in multi-agent systems, with applications spanning from mobility on demand and ride-sharing to kidney exchange. Real-world matching problems pose three significant challenges. First, they may occur in unboundedly large settings. Think, for example, resource allocation in urban environments. Second, they are distributed and information restricted. Agents have partial observability and inter-agent communication might not be available. Third, the allocation must match agents to their preferred resources in order to maximize social welfare, but this preference is exactly what agents wish to hide, which brings forth significant privacy risks. A few years ago, we proposed ALMA, a maximum weight matching heuristic that solves the first two challenges. ALMA is decentralized, runs on device, requires no communication between the participants, and converges in constant time under reasonable assumptions. As you can see, ALMA was designed for real-world, large-scale applications. In fact, in a subsequent work, we showed that ALMA can successfully tackle the ride-sharing and dynamic vehicle relocation problems. We simulated scenarios with up to 400,000 requests and 13,000 taxes. Unfortunately, ALMA, despite being decentralized and operating only on local information, does not provide any formal privacy guarantees. In this work, we introduce a privacy-preserving version of ALMA. Because there is no question that the proliferation of intelligent systems and autonomous agents has the potential to positively impact many facets of our daily lives, but so far we have resigned to the idea that harnessing their power requires massive amounts of personal data to be collected, stored, processed, and analyzed by a service provider. Ride-sharing is a great example of that. We are here to challenge this idea. In this work, we set out to provide a practical and applicable framework for solving one of the fundamental problems of multi-agent systems, finding matchings and allocations, while providing strong worst-case privacy guarantees. Our work shows that harnessing the potential of intelligent systems does not need to compromise privacy. When it comes to protecting the privacy of individuals, differential privacy, or DP in short, has emerged as the gold standard in the past few years. Informally, a differential private algorithm ensures indistinguishability on the output distributions for any neighboring inputs. Let's say we provide two inputs to a differentially private algorithm, which differ only on one element. By looking at the output distributions, an adversary cannot infer an agent's participation. The way this is achieved is by adding carefully selected random noise to various elements of the algorithm. Unfortunately, when it comes to large-scale multi-agent systems with a diverse set of agents, traditional differential privacy is ill-matched. This is because it often requires adding a lot of random noise to achieve a meaningful privacy guarantees, which in turn leads to pronounced drop in solution quality. More often than not, this is not due to the inherent difficulty of the problem at hand, but rather due to the generality of the DP definition. Not only does DP consider a very broad class of adversaries, it also protects all users independent of their characteristics by the same guarantee. While this property is being praised as one of the strongest arguments in favor of DP, it can be completely redundant in many real-world applications for several key reasons. First, users might be willing to disclose less sensitive information, for example, the city of residence. Second, the attacker might already know coarse-grained information because it is likely public or easily accessible, and thus it does not need to be hidden. Again, as an example, consider the city of residence in a mobility on demand problem or the reviewer expertise in a paper assignment problem. Finally, the domain characteristics might exclude a subset of solutions. For example, a taxi in New York would not be assigned to a request in LA, and an expert on auctions would not be assigned to review a robotics paper. Thus, there is no need for indistinguishability between requests on different cities or reviewers on different fields. In this paper, we consider the problem of hiding the utility function of an agent. To solve the aforementioned drawbacks, we develop an application-aware privacy definition called Piecewise Local Differential Privacy, or PLDP. PLDP takes into account the distance between the images of two utility functions. The level of protection depends on that distance. Agents with utility functions that have images close in distance to one another would be indistinguishable from the attacker's point of view. So instead of guaranteeing privacy in the entire domain of agents, which might be quite difficult, we focus on indistinguishability of agents with similar preferences. As you can see in the graph, we fragment the space of utilities into regions and guarantee privacy within these regions, but not between them. A quick note for people familiar with DP generalizations. This might remind you a distance-based generalization of DP called geoindistinguishability. Despite the similarities, geoindistinguishability has only been proven to satisfy basic composition. As a result, the privacy cost grows linearly with the number of privacy mechanism invocations. This is not sufficiently tight for iterative AI and ML applications, which typically require a lot of iterations and thus a lot of invocations of the privacy mechanism. Contrary to that, the proposed PLDP allows to use tighter composition theorems developed for the traditional DP, reducing the growth of the privacy cost from linear to square root of the total number of iterations. Along with the new privacy definition, we also propose PALMA, a privacy-preserving heuristic for maximum weight matching in real-world large-scale applications. PALMA is a privacy-preserving version of ALMA, which means that it maintains all the desirable properties. It's decentralized, runs on device, converges in constant time under reasonable assumptions, and requires no inter-agent communication. More importantly, it ensures indistinguishability under PLDP, providing really strong worst-case privacy guarantees. In the following slides, I will give a high-level explanation of PALMA. Please refer to the paper for more details. In the maximum weight matching problem, we have a set of agents, a set of resources, and a weighted graph representing the utility of matching an agent to a resource. The goal is to match each agent to exactly one resource, such that we maximize the social welfare, meaning the sum of utilities. PALMA is an iterative, randomized algorithm. First, an agent tries to grab a resource. Each agent will select a resource probabilistically with a probability that depends on the utility. To that, we add carefully selected random noise. Suppose that two or more agents select the same resource. Then each agent will independently back off with a probability that depends on his own utility loss from switching to an alternative resource. Again, we add carefully selected random noise to this process too. At the end, we have proven that the system will converge to a complete allocation. Moving on to the simulation results, we have evaluated PALMA in a mobility on demand and a paper assignment scenario using real data in both cases. In this talk, I'll only focus on the first application. Normally, in a mobility on demand application, the process is facilitated by a centralized operator that requires accurate location information of passengers and vehicles, which of course raises significant privacy concerns. Such a problem is ideal to showcase PALMA. First, it occurs in unboundedly large settings. It is obvious that if a mobility on demand provider attempts to naively add noise to protect all users with the same guarantee independent of their characteristics, the achieved social welfare would be as good as a random solution in large-scale environments. Second, it is reasonable to assume an informed attacker, and users may be willing to reveal approximate location information. As an example, There is no point in attempting to guarantee indistinguishability between two agents in different cities. Instead, we focus on indistinguishability of agents with similar preferences. To give you a concrete idea of what that means, this is the map of our simulations, and the overlaid rectangle denotes a fragment of the utility space. All agents in that area are indistinguishable from the attacker's points of view. The attacker can still infer that you are in that area, but not your exact location. And this is not a small area. It corresponds to 730 city blocks, and its length is 4 kilometers, larger than the width of Manhattan. Moving on to the results, let's begin with the privacy cost. The figure on top shows the maximum and the median per agent epsilon for increasing privacy region size, and the figure in the bottom shows the histogram of the per agent epsilon values. Informally, epsilon denotes the privacy cost. Lower epsilon means higher privacy. Palma provides really strong privacy guarantees. Specifically, the median epsilon for an agent is 0.4, and intuitively, this means that an all-powerful attacker can distinguish an individual with probability of only 0.59, meaning practically random. Finally, in terms of social welfare, there is of course some degradation to the solution quality due to the introduction of random noise, but as you can see, Palma still manages to achieve really high social welfare, up to almost 85% of the non-private optimal solution. As a baseline, the maximally private solution loses almost 50%. To conclude, there are three main contributions. First, we introduce piecewise local differential privacy, a variant of differential privacy designed to protect the utility function in multi-agent applications. PLDB enables significant improvement in solution quality and strong theoretical privacy guarantees, while being applicable in real-world unboundedly large settings. Second, we propose Palma, a privacy-preserving heuristic for large-scale maximum weight matching applications. Third, we evaluate Palma in a mobility on demand and a paper assignment scenario, using real data in both cases. Palma is able to provide a high degree of privacy and matchings of high quality, up to 85% of the non-private optimal. Thank you for your attention. I really hope you enjoyed the talk, and I look forward to discussing with you.